Good morning, everybody. All right, the coffee is sinking in. So thanks for having me. It's my first time at the exchange, and hopefully after 30 minutes you won't decide it's the last time. So it's always kind of energizing to be in these meetings, see some old friends, make some new friends, and talk about what we're all passionate about, which is quantum computing. What am I going to do today? Well, today I'm going to talk about my admiration for how this hub has grown, what we're doing in the company that is well aligned with the goals of the hub. And I'm going to then finally close out with what we think we'd like to do with the hub moving forward. Is that an okay agenda? I only see my folks nodding, so you guys don't have a choice. You have to listen to whatever I say. So let's talk about building the leading quantum zone. I think when you heard the governor this morning, you heard it very clearly. If you didn't, then I had the privilege of spending a few minutes with the governor before the meeting started. And he made it very, very clear that of his belief in quantum and his desire to see Chicago and Illinois be the center and a leading contributor to that revolution, which was music to my ears. And then he asked a really interesting question. He said, key components, what are the key components for a successful quantum ecosystem? Right? And it was about 8:01 a.m. I hadn't had my coffee yet, so being tested by Governor Pritzker was a good wake-up call. But what it turned out is I kind of went through my answers of what makes it successful, not just a hub, but a successful hub. And you'll see behind me, or if I can see that straight, you know, the usual culprits, if you will, of an ecosystem. Governance, policy, regulations, capital funding and investments, building the workforce, talent, connected research networks, because collaboration is so important, and then an industrial base. Without that, what we've learned, I've been in high-performance computing for 30 years, is you start to build solutions looking for problems. So having an industrial base, having use cases, having their active participation in shaping the technology and also selecting the right winning technologies is a very critical part of both the technical and the economic progress of a technology like quantum. So then we started talking about the Illinois Quantum Foundation and all the assets it brings to the table. Particularly, I'm not going to repeat the things you already know or you heard the governor speak about, but it's a very deliberate choice to build these, connect these, and we think grow the seed of a really important effort to accelerate quantum computing or quantum technologies more broadly and bring them to market to create economic value. I mean, that's really at the end of it why we're all here. So then you ask, okay, then I'm kind of walking you through my conversation with him, but then we said, okay, we're ready to ignite now, right? I mean, the powder is all there, the elements are there. What do you do to ignite that? And what you really now need is an operational quantum hardware and software stack so that people can start, whether you're a researcher in hardware, you can get a good view of what state-of-the-art things are, as well as learn where some of the challenges are. Maybe it's in quantum error correction, maybe it's in some other areas of the hardware in improving physical fidelities, maybe it's in improving speed, maybe it's improving the architecture around all-to-all connectivity. But there's a host of things to work on in these early days of quantum computing, and I dare say will be for the rest of the time we live in quantum computing land. And then, of course, there's a software. And by software, it's a pretty loaded word, right? Software, there's the things that make hardware work. And then there's the software that makes all of that worth it, which is applications and use cases. So that seemed like an operational quantum hardware and software stack that can be both useful for research, but also, remember that circle, can also be very, very useful for end users to start seeing a path, if not value itself, from this technology. So of course, the question is, how far are we from this today, right? And again, if you listen to different parts, you may have your own ideas. Jensen kind of lighted this space up about a year ago when he said, oh, it's 15 to 20 years away, and then obviously, since then, his opinions have changed. There's still the glass half empty, half full, but it's no longer a question of if quantum, it's become a question of when quantum. And that is a very important transition for this technology base to hit. And that, because that transition, there was a very interesting point made this morning about the financial awakening of the quantum industry would not have happened if it was still in the if stages. Yes, it would have been there, but not at the levels we are seeing today. So now if it's a question of when, well, what is when, right? Is it 15 years? Who believes it's 15 plus years out to significant commercial value? All right. I wish I was staying longer in Chicago today. Who believes it's in the next 1 to 3 years? So the rest of you are somewhere in between, right? I can do my math. Okay. Well, I'm with you, the rest. And I'll be very open about it. It's not because I like the comfort of larger numbers, but that's where we think the path is for massive creation of commercial value in different end markets, different use cases. I kind of wanted to go into why we think, if you'd asked me this question 2 years ago, or maybe 3 years ago, and said, when quantum, and I just started reading about noisy intermediate scale, or NISC, as it was called, is it still called? The answer might have been 5 to 10 years out, or 10 to 15 years out. I might have actually agreed with Jensen, right? But if you look at where we need to be headed, and sometimes our answers are conditioned by where we need to be headed and how far that is, it's where we're really heading to is the need for a universal, fully fault-tolerant quantum computing at scale, or a computer at scale. And I was particularly taken by the last presenter, the ex-chief scientist of Australia, who had one very nice slide, which said, it's not about who gets there first. It's about who builds something that everybody can generally use, right? And that doesn't happen just by technology. I could show you an optical table full of all the gizmos in the world and tell you it achieved 4 nines in 2-qubit gate fidelities. And then you would say, well, what algorithm can I run on it? It's like, yo, wait, don't touch my machine yet, right? That's not a useful quantum computer. So when do we get there? And what are the steps that we need to get there, right? My contention is that the universal, fully fault-tolerant quantum computer is actually here. It may not be at scale, but the recipes to create universality, I never get that word right, but you know what I mean. Come on, help me out. Fully fault-tolerant, or a path to full fault tolerance is here. The recipes are known, and now it's about scaling, which is why we are now exiting the era of discovery and research, if you will, to the area of scaling out these technologies, maturing them rapidly, and creating economic value or commercial value. And it's kind of poetic justice that that happens in the International Year of Quantum, which is this year. And I know you and I met in Paris earlier this year to celebrate that. So we are at the doorstep of the quantum era, and I assert this by saying the recipes for building those computers that we talked about in the last talk that people can use, they can use to do different kinds of things, use it effectively, use it in a trustworthy manner. That era is no longer 3 to 5 years out. It's here. The recipes are known. Now, if you challenge me as to why I say that, I'm going to spend a little bit of time telling you why. The quantum era's recipe, that recipe to get to a universal, general purpose, accurate, fully fault-tolerant quantum computer, you need at least 3 things. You need scalability. You need to be able to get to large qubit counts without tanking the accuracy of the machine. You need accuracy. And particularly at scale, as you get scale-driven errors, if you will, things like crosstalk and other phenomena become far more acute to manage. You cannot forego scalability and accuracy and trade one versus the other. And then you need universality. There, I got it right, even though at a slower speed, which is really, you know, I come from a semiconductor background, and if someone gave me a design and said, by the way, you can only use these design rules, so that's like having a computer that can do addition and subtraction and no multiplication and division, right? I mean, it's like, write all your multiplications as additions, maybe. So that is important, but we are forgetting something if everybody is going to be able to adopt this technology again, whether you adopt it for research or commercial use, which is around programmability, right? I have spent 30 years in classical computing, and I remember the days of the GPU when it first exploded on the scene, or maybe a small little explosion on the scene. Everybody walked around saying, oh my God, it is so hard to program, right? You have to, after years of spending yourself freeing from things like explicit memory management, where you happily lived with higher level abstractions of declaring data structures and having the underlying system manage things like overflows and checking for those kinds of things, now we were back to managing, and bad things happen when you didn't manage them properly. Right? Really bad things happen. Trust me, I've done a few of those. So getting to these higher level abstractions that still allow for that improvement in productivity, readability, maintainability, but not giving up. One of the underbellies of abstractions is you give up the ability to program the metal. I'm not sure we can say program to the metal for quantum computers anymore, but you know, you program to the basic things. And you have to find a way to do that while you are abstracting these layers and these representations of physical machines, but not lose access for the programmer to the very specific hardware features. And that is it's as much of an art as it's a science. But that is necessary to wrap around these speeds and feeds, if you will, in the bottom 3, for you to have a quantum computer that people actually can use. So if you go through it, you know, a lot of why I claim we have the recipes is a lot of research went into it over the last decade, and that research is coming to reality. If you look at scalability, for instance, we've got pathways now in line of sight and test beds and architectures that you can get to, you know, absolute millions of qubits. And in fact, some of the DARPA programs are exploring multiple ways to do that. And it has to do less with the qubits as it has to do with how you manage, control, and wire the qubits, if you will. And in doing so, also not making the problem explode. So the other thing is that you build qubits, you build more and more qubits. And you know, if you looked at some of the Google results from last time, I did a short calculation, and if you get 104 qubits giving you one logical qubit, then how many do you need for a 1,000 logical qubit machine? It's in like hundreds of thousands. So while you have to improve the physical scale, you also have to look at overheads of generating logical qubits so that the machine doesn't become uncontrollably large. So those are the kinds of things that a tremendous amount of research, not just at Quantinuum, other places have gone in, and we see a clear line of sight to building larger and larger qubit count machines without sacrificing complexity or fidelity. We, at least at Quantinuum, are very confident of that. The second thing is around accuracy. If you look at accuracy, it's, about even 2 years ago, people were talking about error mitigation only because both detecting the errors and correcting them seemed quite a decade plus long travel direction. But we've proven that you can do real-time syndrome extraction and decoding. You've got a tremendous amount of growth in what I would call QEC codes, right? Including now generational improvements where you concatenate codes. So if you had error detection codes in the past, you're getting higher throughput by actually concatenating them, combining them. And then most importantly, which we demonstrated, was fault-tolerant universal gate set. So many people said you could do Clifford gates, but what about non-Clifford? This is the part which is like you don't have multiplication division on your machine, right? Because they're really hard to get fault tolerant. But now we have the recipe and we've proven it that you can Clifford and non-Clifford gates, you can get fully fault tolerant. That doesn't mean error free, but what it means is all operations on those qubits will improve with error correction, with rounds and rounds of error correction, right? So you can get towards fault tolerance. If you look at universality, I got it right the second time. We've obviously shown logical qubits. We've shown logical qubits with the universal gate set, which includes non-Clifford gates. And so that we believe that we've kind of exited the realm of special purpose machines that forces the programmer to think of the machine first before they think of their algorithm, to thinking about their algorithm, giving them a full set of recipes on the hardware to operate with. And then finally, programmability. This one, being a software engineer, and I was never smart enough to get admitted to a hardware program in quantum mechanics, so I stayed with software. Is probably the place where, in the early days of a technology, when you're just trying to make the damn technology work, you don't pay attention to this. It's like, sorry, buddy, you got to code in circuits, right? Or you got to think in terms of gates. I can guarantee you that if I went to a bank today and people who are doing credit risk modeling, and they're looking at large stochastic problems and graphs, they don't think about gates. Right? I mean, at most you might get a question like, Bill, what is he doing with quantum computing, right? But to connect quantum computing to people who don't speak the lingua franca of the hardware, you have to build a software stack. And that software stack has to have two things. One is expressibility. You need to be able to express the software, your algorithm, in the most expressive way possible that maps to the best features of the hardware. So you need to be able to say, well, if I believe that my algorithm benefits from mid-cycle measurement or conditional qubits, that I have a programmatic way of accessing those features. So you must have expressibility. The other is you must have functionality, right? So if you're going to do real-time error correction and your software and your infrastructure layer, your runtime, does not allow you to do that, then it's a good, interesting concept in theory, but you'll never do real-time error correction. So building a real-time control system, putting a developer suite on top of it, and most importantly, coming up with a language that doesn't sound like, to me, it's really, when I first looked at how people wrote code, they would draw circuits for me. And I would be like, oh my God, this takes me back to writing the towers of Hanoi using machine code, where I had to actually look up what does move A to B look like in hex, right? Hexadecimal, in case the mic's not working. So that is the other big transition we made from research to reality. It's no longer about just making the damn hardware work. It's about making the hardware usable, right? And we at Quantinuum are very proud of the fact that we have a full stack now. And this stack actually works across multiple hardwares, right? So because of the levels of abstraction, as long as you're gate-based, we don't do what's called the processor ID check. Your performance may vary depending on different endpoints you run on, but this is a software stack that lets you write your algorithms and test on multiple pieces of hardware. So when I'm doing a short cover over the work of many, many people that is a culmination of decades of research, but I assert to you that for those sitting here thinking there's still some time to go before a useful quantum computer shows up on which I can do my research or my development of use cases, you're wrong, right? That is here, and you need to get engaged today. So what's next then? What's next is very simply our experience, or what I'm going to say to you next is born out of our experience of at least in 3 places, building these quantum ecosystems, one in Singapore, one in Japan, one in Qatar, is you really have to start to look at what is going to pull the value out of it. What are the groundbreaking applications? And you know, too long, and this may be a controversial statement I make here, too long we've been kind of stuck in this notion of what is quantum advantage and supremacy, right? Frankly, I think it's done the community and the industry a disservice because it's pitted quantum computing as a versus another form of computing, which is classical computing. And that's really not what quantum advantage is. Your advantage from quantum computers is using quantum computers as part of the solution. You're doing something you couldn't have done before. Either achieve levels of efficiency, either in resource efficiency, or doing things you could not have done economically or even technically ever before, right? So that is the nature of quantum advantage. It's not about, can you run this algorithm and it, you know, on a quantum computer in 40 seconds that takes 10,000 years on a supercomputer. It is, can you discover the next drug for under $1 million in 30 days? That is quantum advantage. And if quantum is part of that solution, without which it couldn't have been done, it doesn't have to be the classical computer. That is our belief. That is what we are seeing as we look at these groundbreaking applications and what they need. This is Amdahl's law applied across computing types. Remember Amdahl? Poor Gene Amdahl? Where he said there was a parallel part and a serial part and what speed up you got depended on the fraction of those two. Well, this is like Amdahl applied to classical and quantum. There will be some portions of it that are extremely classical friendly. And you don't want to, just for the sake of proving quantum's worth, try to run them on a quantum computer. There will be things that quantum computers do expressively well that classical computers would not be able to do effectively or at all, and having the quantum computers work with the classical computers is the right way to go. That's what we're seeing as we look at use cases all the way from chemistry to large data optimization problems, and pretty much everywhere we go, we run into this particular area where it's hybrid computation of quantum plus classical that solves the problem either in ways that you couldn't solve before or at cost levels that now make it an economic technology, right? I'll give you one example. Today's, if you look at drug discovery, for instance, right, it's well understood. You do front-end discovery, you just do discovery of molecules, you discovery of bio and molecular interaction, then you say, okay, I've got a drug. Then you apply a patent, your patent life starts, and then at some point you do wet lab, you build those molecules, and you go into some level of testing. Well, from the time your patent is issued, or you at least file, to when you can actually put the drug out in the market is somewhere between 5 to 9 years. Sometimes it's longer than that, but I'm talking about median, right? So you've already lost half your patent life in trying to get this drug out. What we are seeing is quantum computers shorten that life's to value in 2 ways. One is, of course, that actual search for that material is far more chemically accurate using quantum simulations, and so you hit the answer sooner. The second is some of that analysis is actually useful to get your regulatory stuff done versus having to run oodles of longitudinal results to produce the same assurance. Now, if you were making $50 to $100 billion on a drug, which, by the way, those are eye-popping numbers, but you should go check how much Ozempic has made in 3 years of existence. It is 2 digits with a B at the end of it for the company that made semaglutide Ozempic, right? And so if you give them 1 to 2 years of patent life extension, that is high single digits to higher than that estimates of economic value created for them. And so even a $500 million, $1 billion quantum computer to generate $10 billion of value seems like, okay, that's not a bad deal, right? So as I was saying, we run into, in all of these, many of these use cases, I would say, maybe not so much in cyber, we run into how, the world's already adopted AI, so how do you do better, right? Again, back to this quantum advantage supremacy, almost false battle. And what we find is people have already said, look, we're going to use this tool called AI, but we have challenges. We have challenges of accuracy. We have challenges of even understanding that it's doing, what it's doing and why it's doing it. We have challenges of not being able to use it in certain places effectively because we can't train it, right? We don't have the data. Where we have the data, we've trained it. Well, one of the big breakthroughs I believe will define the next age of discovery is Gen Q AI, where quantum data is actually used to train classical LLMs with information they could have never had before. This could be in large molecular, large multi-body interactions, force fields, or excitation energy levels for different levels of stimulus that, and then you look at the applications you can build, such as new materials for drug delivery, where instead of trusting, when it says on the side of the box, this is a long release capsule, which is essentially you're leaving it to some material that melts in your body at a certain rate. Now you're actually designing drugs for very, very fine kinematic release, only in the right spot, in presence of a stimulus. And so it's these kinds of things that need the quantum simulation to train the classical LLM. Again, it's not about using quantum computing to actually run the transformer-based, say, LLM, but it's what did you train that on in order for it to have that effectiveness and trustworthiness to solve that problem. And we believe this is the next big revolution of not quantum fighting classical AI to assert supremacy, but actually working together to achieve something that neither of them could have achieved alone. And this is the underpinning of many of those breakthrough applications or application ideas we are seeing today. Humans, now advanced with AI, and a, no pun intended, quantum leap forward with AI plus quantum. So with that, I'm going to end by saying the governor had said our vision to become the epicenter of the quantum ecosystem is becoming a reality. I would assert that if we take that becoming out, put an operational stack in the hands of the very talented researchers and industries in the corridor, then we would actually achieve warp speed acceleration of this hub. And we at Quantinuum would be proud to do that. Thank you.
Thank you very much, Rajeeb. A quick question.
We got time for one for sure.
Over there.
Thank you for your thoughts. When you say the recipes exist for universality and fault tolerance, that kind of then leaves the scalability and programmability remaining. In terms of coming up with these viable commercial solutions, which do you think still needs to have priority or preference, scalability or the programmability?
Well, unfortunately, you won't like my answer, but my answer is if you keep building more qubits and you don't improve the logical error rate, you will serve. We are already at a point you can do a few things. You just want unlock the larger set. So, the industry has said 100 logical qubits is roughly a good milestone point for many applications, not just say, I want to do X, but if you look at the different end markets, now you have a viable solution. It's kind of like when MS-DOS first was able to address more than 640K, right? So our goal has always been to add usable qubits, not add qubits that either gave you no error rate value, or add qubits that frankly made it more expensive to manage them but didn't provide the benefit, right? And so that, I think, is the way to go, is not detach both of them, but to attach them. And particularly as we get to universal gate sets where you have to maintain things like magic state factories, right? Your ability to have higher and higher physical fidelity qubits just helps that problem, because you will suffer lower overheads in kind of those overheady type things that you're using qubits for. So that is what we believe. We believe that many of those applications will require lower error rates. That's what we are targeting on our roadmap, as they need more qubits. And if the world focuses on just adding qubits or just lowering error rates for current qubits, I think we would be in the quadrant. If you think of a 2x2, we'd be stuck in the left bottom quadrant. And while that is useful, you have to look at what you're missing if you don't go down the diagonal path.
Thanks, Rajeeb. Thank you for a great talk.
Thank you.